Boom! Alright folks, Hume here again. How are you going? So, welcome to yet another in our series of videos where we're dealing with circle theorem and C-Sec mathematics syllabus. We have now two more theorems. We have theorem 6 and 7. So this is 8 and 9. 8 and 9. So we had 1, then we had 2 and 3, then we had 4 and 5, then we had 6 and 7. So this is 8 and 9. So we're doing two theorems in this one video. Alright? So, theorem 8. The lengths of two tangents from an external point to the points of contact on the circle are equal. Right? So basically, how that theorem would look diagrammatically is that you have one point here. Let me call that point T. Alright? This is the external point. We could call this E. We call it E now, man. E for external. I like to name things in a way that will allow us to remember it, right? E for external, alright? And we have the points of contact AB. So, the lengths of two tangents from an external point. So, you have one external point, and you have two tangents from this point. Now, the way the geometry is set up, from any point outside of a circle, you could only ever have two tangents coming from that point. You can't have more than two tangents. Alright? So, two tangents, the lengths of two tangents from an external point to the points of contact on the circle are equal. So, in other words, if B is the point of contact for this tangent, let me call it BE, and A is the point of contact for this tangent AE, then AE is equal to BE. Alright? So if we have to write that down, we would say AE is equal to BE. Alright? And that is all. That is all there is to that particular theory. Of course, if we were to join A to B and make a chord, then let me do that, right? Because sometimes you might get this in a problem. You might have, for example, I just put it in dotted lines because we're really not too concerned with this here, but I just showing you what could happen in an actual question. If I were to join A to B, this AB here would then be a chord. And because BE is equal to AE, it means therefore that triangle AEB is an isosceles triangle. Alright? Where this angle here would be equal to this angle here. So in other words, if you have a situation like this and you know what this angle is, by virtue of the fact that if we are told or if we could show otherwise that BE and AE are tangents, then if we know this angle, then we could find this angle, these two angles, each of them. And then, because this is a chord and this is a tangent, then this angle here would be equal to any angle that this chord would subtend in this segment. Same story here. Because this is the same chord and because this length is this length, giving us an isosceles triangle. And if this angle is equal to this angle, then this angle too would be equal to any angle that the chord will subtend anywhere on the circumference of this circle in this segment. Alright? So, I went through all of that extraneous stuff. Right? Just to make the point that everything is connected. So, you get theorem 8. It is highly likely that you'll get this sitting by itself all alone in a question. That is almost guaranteed not to happen. If you get this, tell yourself you'll have some other lines jigging across here. And you'll have to interpret this theorem in tandem with maybe 2 or 3 other theorems at the same time to solve whatever problem you need to solve. Good? Excuse. So what we do generally is we separate each theorem, we present it, right? We try to give practice in each particular one by itself. And then we get to the point now where we throw a whole question, boops, and you have 2 or 3 theorems at the same time. There is no telling really which theorem or which theorems they will throw at you in a particular question. You have to take each question on its own merit, decipher it, and move on. Good? Right, so theorem 9. So this is the final theorem in the list on the 2018 mathematics syllabus, CXC. It says that the line joining the center of a circle to the midpoint of a chord is perpendicular to the chord. Good? So the line joining the center to the midpoint is perpendicular. So if, now again, they will give you sufficient information in the question to allow you to determine that this M is actually the midpoint of the chord AB. Alright? So in other words, you do not have the luxury of assuming. So if you have a chord, if you have a line from the center and it meets a chord, unless specifically told that the line from the center cuts the chord at the midpoint, or unless there is other information in the question that will allow you to deduce that the point at which the line intersects the chord is the midpoint, do not assume that, even if it's looking like that. Alright? All of these are little tips and tricks in solving these questions. If, however, you are told from the outset that the line cuts the chord at the midpoint, and you are also, or you have information in the question that will allow you to deduce that this point is in fact the midpoint, we call it M, then yes, at that point we can now invoke theorem 9, which is the final theorem, and say that the line joining the center of a circle to the midpoint of the chord is perpendicular to the chord. Alright? And the implication, of course, just as we had over here, if you have a situation where, let me say, you have a radius from the center to one end of the chord, and a radius from the center to the other end of the chord. If you have that, then because, come here, let's straighten this line, man. Let me look at least look straight now. Straight. It's looking a little more straight. Not as straight as I would like it to, but can't fuss too much about that now, right? So if you have a situation where you have a line from the center joining the chord at the midpoint, and let us say for argument's sake you have a radius OA and a radius OB forming a triangle, and this is now the triangle OAB, then you know that this too is an isosceles triangle. And because this here is a right angle, you're now in a position to go back to your regular trigonometry in section 1. Your right angle, trigonometric ratio, sine, cosine, and tangent. You have your hypotenuse, you have your adjacent, you have your opposite, adjacent, opposite, whatever. Depending on the angle, they might give you the angle here. In which case, this would be adjacent, opposite, adjacent, opposite. In both cases, the radius will be the hypotenuse, if you have a situation like this. But that is, again, that is just a little extra in terms of planting the seed in your mind, so that you understand that it is hardly likely that you will just get this theorem sitting all on its own. This is what you'll almost certainly have. A lot of the questions where we invoke this last theorem usually call for manipulation of an isosceles triangle somewhere inside there. Alright? So we consider the theorems, we consider the extra information. So what I will now do is rub off the jagged lines and go back to the original theorems, and we round off the video with that. Alright? So we go back to square one. And we round off the video by simply enunciating the theorems again as follows. Theorem 8. The lengths of two tangents from an external point to the points of contact on the circle are equal. External point, point of contacts, length of line equal lengths, right? You may get the little, now, no, in a circles question, they probably will not do that. No, yeah, they probably wouldn't get that in a circles question, because if they do this, they will practically be giving it away, right? So in other words, in a circles question, don't go looking for that. If you get it, then count your blessings. If not, then they expect you to know this particular theorem. All right? And then, of course, the final theorem is that the line joining the center of a circle to the midpoint of a chord is perpendicular to the chord. All right? Center of the circle O join to the midpoint of the chord AM. Sorry, the midpoint of the chord AB is the point M. So OM is perpendicular to OB. The line joining the center of a circle to the midpoint of a chord is perpendicular to the chord. End of discussion. All right, so this has been a nice series of videos where we presented the circles. All right, this is one of the things that I've wanted to do for a long time, because I have felt in the course of my teaching that there are things that I can say about the circle that students probably will not get in other places. There are ways in which I could explain the circle. There are ways in which we could flesh out the thing and break it down that you probably will not get in other places. All right? Yeah, so I hope that you would have enjoyed it. I hope that you would have understood the thing in a clear and concise manner, and you're now in the perfect position to take your understanding to the next level by finding questions and practicing. All right, so all the best with this particular topic, and I hope that you stick around for the other topics, because we have plenty more to come.